it is my pleasure to introduce Dr. Mohammad Alfrad Nobel. He is a tenure track assistant professor from Louisiana State University. He's from the health department in Freeport. Is that correct? Thank you. And he is going to talk to us about how to design and understanding your data and performing statistical analysis.
Okay, thank you, Dr. Alvaro, for your introduction. So, and also I'm thankful for giving me the opportunity to present some of my work here. So I'm an assistant professor in the Louisiana Department of, Health Science Center in the Department of Internal Medicine. So here we do a couple of interesting things, but my main focus of research is actually right now is image processing for both Alzheimer's and drug abusers patients. And also we do a lot of health related statistical analysis too. So here on this presentation, I'm going to talk about how to design a study, understand your data, and perform statistical analysis. So the first outline of this presentation is how you can design a study and different statistical terms and concepts for data analysis. Right now you guys are much more familiar with traditional statistical analysis like linear regression, t-test, ANOVA, chi-square. But there are some other area of statistical analysis I want to explore. I want to show the results. And I'm pretty sure that some of the things you may have seen, but some of the things are pretty much new and interesting so that you can see what we can do with our data. And I'm also going to talk about geospatial analysis, machine learning, and bioinformatics. So at first I want to put emphasis on steps of a research. So we find a lot of students, a lot of residents actually come to me right now. I also have a postdoc, MD PhD student as well. So they come to us and say that, okay, how should I design a study? How should I do a research? So when you want to perform a study or a research, the first pivotal thing is identify your topic, what you want to talk about. Do your research about. Is it any kind of disease? If it is a disease, what kind of disease it is? What kind of patients are actually infected by that one? And suppose if I talk about drug abuse, when you talk about drug abuse, the first thing comes up like, what is the current trend of drug abuse? Which drug is more prominent? Which age group, which race, which gender are more affected by these drug, right? So this is your research question. And then you have to identify the location of your information, how you can get the data. So are you planning to do a retrospective study, like where you have already emergency health record and you can use those data, or you are planning to perform a clinical trial or prospective study? How you are going to collect the data? After you decide that, okay, where you get the data, what is the source of your data, then you have to think of, after you get the data, how to perform analysis, which statistical model is right. There is no right or wrong. You can use any of the statistical method, but some of the things you have to take, or you have to think beyond the box so that the result becomes something new and interesting. And then finally, you have to write down the results and then put the references. So this is a circular process of research. This is called direct acyclic graph. You can see this is one way, circle. You cannot go back. So the first thing is your question. What is your research question? What is, then it will come to how to collect the data. Who will be in the data set? Are we going to talk about only one specific group? Are we going to take care of only adults or overall? Collect the data, then perform the statistical analysis, and finally write down the results. So this is what very important thing in statistics. the success of your research doesn't depend on your conclusion. If you find something significant, that doesn't mean that you are valid. So you have to be very careful about the validity of the test, which is type 1 and type 2 error. The type 1 error is false positive and type 2 error is false negative. So when you tell someone, okay, you are telling a male patient you are pregnant, that means he's false positive, right? And when you are saying that a female patient who is not, who is pregnant, but you're saying you're not pregnant. So that's why it is very important that how you are defining your test of hypothesis and how you are explaining the results. What is the accuracy of your result? And also in statistics, you'll always see that people talk about 95% confidence interval and alpha equals to 5%. What does it even mean? So 5% alpha means how much error you are actually allowing in your estimate. So when we say that my alpha is 5% or 0.05, that means my estimation may be wrong 5 times out of 100 times. If I do the same analysis on different data set, out of 100 times, 95 times we'll get this result. And 5% time, maybe we will get different result. And what is this 95% confidence interval? So if you really do the analysis and you see the results or the parameter estimates, it will be 95 times out of 100 times within that boundary. So that's why you define a boundary that how confident you are. In statistics, you will also see one thing called power. And that power is actually coming from this alpha. How much you are confident that your estimates are right. That's why when you perform a clinical trial or a prospective study, we always have to calculate the sample size and power so that we don't lose time and our money. So there are different types of statistics. So first one is descriptive statistics and another one is inferential statistics. So all of you are actually familiar with these descriptive statistics, where descriptive statistics means you are trying to identify the description like mean, median, mode, number of people male, and number of people female, mean age, median age, which group is higher than which group. But that doesn't let you do any kind of prediction, any kind of inference. If you want to do any kind of prediction or any kind of inference, you have to do this inferential statistics. What actually belongs to these inferential statistics? Any kind of regression, logistic regression, linear regression, nonlinear regression, any kind of things, any kind of modeling that you can use for any kind of inference or prediction is called inferential statistics. So these are a couple of types of study that I want to emphasize. One of them is called prospective study, where you design a study that, okay, you are going to collect the data. You design a questionnaire and then you collect the data. That's called prospective study. For any clinical trials, we use prospective study. Retrospective study is you collect the data, already data has been there. Like data has been collected, suppose emergency health record, you just go and take the data from there. So this is called retrospective study. Case control study, where you have a group of case and you want to compare their comorbidity or their different parameters with the controls. The case is, suppose you have a cancer patient and you want to give them a medicine and you want to see with this medicine and another medicine, how they are different between case and control. Case crossover study. So the crossover study is another one. This is an updated version of case control, where the same person works as a control for the case. So suppose when the patient got a disease, they got some medication. After that one, we give a washover period. And then the patient, we compare when they recovered, before recovery, we compare the same person. This is called case crossover. Cross-sectional data. So cross-sectional study when we have a specific time point. Suppose we want to do a research on 2020 or 2018 or 2018. Any specific time point is called cross-sectional. Randomized control trial. When you have a clinical trial or you want to randomly select a patient and put that person in a group, it's called randomized control. So you randomly select a patient. You don't just go or select someone. You have this one, randomly you take one and put in one group, and randomly take another patient and to put them on another group, which is called randomized control trial. Some types of variable. These are the common terms that you will see. I'll also talk about some of the interesting things later on, but I want to give some feedbacks or ideas, like what are the common things you will see in when you want to do a statistical analysis. So there are 4 types of variables you can see. One of them is called categorical. Another one is ordinal, survival, and numerical. So what is categorical? When you can order them, or when you can put them in one of the category, suppose male, female, diabetes, blood type, you can put them in different categories. That is called categorical data. Ordinal data, when you have Likert chart, so where people say that I agree, disagree, I have no opinion, I don't care, whatever. Or cancer stage has 1, 2, 3, 4, where you can order the response. It's called ordinal data. Survival. Survival is in a sense that you follow up a patient, and after a certain time period, you see that the patient actually survived or died. Or you want to see whether the patient has been improved from the diagnosis, from the disease or not. You can define that one as a survival. Numerical data, discrete and continuous. So where you have, continuous measurement, or you have a discrete measurement. And also you will see a lot of things between called parametric versus non-parametric. So what is this actually? Which one is actually better? So there is no way we can say one test is better than another one, because every test has some statistical properties. If it follows those properties, we can say that, okay, these method will work better than the another method. So for the parametric test, the main assumption is normality. So sometimes when we do research, we see that our sample size is very low. Suppose 5, 10. If you look at the basic science researchers, there are 5 different mice, 6 mice. If they do a normal test, it will never fulfill their normality assumptions because sample size is very low. It doesn't mean that the data is not valid. So on that case, what we have to say, we used parametric test, we can do that one, but at the same time, we have to do non-parametric test as a sensitivity analysis, just to show that both the results giving similar kind of result, estimates. They may be different, estimates may be different, but how different they are. One test is saying significantly higher, improving. Another could be another test is saying significantly it's decreasing, it's not improving. That means like they're talking about 2 different directions. On that case, we have to be very careful and see that, okay, why we are getting that result. Other than that, both of them are okay. For parametric test, it has more power because it depends on assumption, normality assumptions. On the other hand, non-parametric test doesn't depend on any kind of distribution. You don't have to worry about the distribution. So these tests are actually robust than parametric, but less powerful. So these are some common tests you will see that in statistics. These are parametric tests for sure. I didn't put the non-parametric, but for this non-parametric for pair t-test, suppose the pair t-test, when you want to compare the mean between 2 groups. Again, I'm saying you are comparing mean, nothing else. So when we do non-parametric paired t-test, alternative of these parametric test, non-parametric test will be Wilcoxon test. On Wilcoxon test, what they will do, they'll compare the median. So, here on pair t-test, we are comparing the mean. Non-parametric Wilcoxon test will compare the median. We also do unpaired t-test. We also do ANOVA. So what is the difference between t-test and ANOVA? So when you have more than 2 groups, you cannot do paired t-test. On that case, we have to do one-way ANOVA. When you have 2 multiple groups, suppose you want to see the difference for group 1, group 2, group 3 for male and female. On that case, you have to do 2-way ANOVA because you are also considering the gender. This is some common type of regression you will see. linear regression, when you say that the response and the outcome has a linear relationship. Over time, you suppose you want to see the relation between age and height. So if we take age from 0 to 25, we'll always see height is increasing with age. There's an increasing trend. So we can run a linear regression. Logistic regression, where your outcome is binary. Suppose you want to say that one cancer patient versus non-cancer patient, smoking has an effect on cancer or not. So on that case, your outcome will be cancer, yes or no, smoking, yes or no. And then you want to see if there's an association for adjusting for age, race, other variables. Lasso regression. Lasso regression is actually for variable selection. When you have like 15, 20 different variables and you don't want to use all of them, then you want to select which variables are important based on lasso regression. There is also some other regression called stepwise forward regression or backward regression. However, I'm not going to in depth of those things, but I'm just want to give you some idea that these are the common terms you'll see and what does it even mean. Number 4 is principal component analysis. Another term is called PCA. This is also a dimension reduction method. What it does, when you have, suppose you have a gene sequence data, there is millions and millions of genes. All of them are not signals. Some of them are signals, some of them are actually noise. On that case, we need to identify which are signal. And that big data set is really very difficult to analyze in normal computers. We use mostly supercomputer to analyze those kind of data. And I'll show you one of those in future slides. Poisson regression. So Poisson regression is when you have count. So suppose you say that in Georgia, different county in Georgia, how many people died on COVID? You have total numbers instead of any single value. On that case, you cannot use linear or logistic regression. On that case, you use Poisson regression. Again, if the value is over dispersed, that means the variance is very high among the data, then you cannot use Poisson. So if improvement of Poisson regression is negative binomial. And the last one is called Cox proportional hazard model. This is very important model for survival analysis. When you suppose a cancer patient, you want to follow up for 5 years. Over time, within that 5 years, a lot of patients will recover and a lot of people will die. And we want to see that specific drug has an effect on their survival or not. So if you want to do that one, then we have to do Cox proportional hazard model. And this Cox proportional hazard model has a couple of assumptions. The first and very important one is the proportions are hazard. I mean, the proportion of those events or the hazard is, that is called hazard, are proportional to one another. Okay, so we have some tests for that one. If it doesn't follow that assumption, we cannot use Cox proportional hazard model. However, this is a different and interesting area of research that I would like to emphasize. So this is called geospatial analysis. This is also, you can see on different literature, they're called small area disease modeling. So what we do actually on that one, so suppose we want to see like how the disease varies over time and space. That means suppose the effect of COVID may be different in Georgia than Louisiana. Again, that effect within Georgia may be different from one county to another county. So space and time has some effect on health data. So that's why we actually use geospatial analysis to identify the spatial pattern or trend. And we use the real world data like geographic location to identify the disease pattern. So this is an example data that we wanted to see COVID vaccination rate and region in Louisiana. So we collected the data from Louisiana Department of Health, and we wanted to see, okay, if I move from one region to another region, do we see a different vaccination record in Louisiana? Does it has to do anything with their socioeconomic factors, lack of facility, and their deprivation index? Okay. So this is the table. You can see the total number of population, total death, mortality rate, series completed, and vaccination rate. So series completed means like in Louisiana, everyone got Pfizer vaccine. So any who has completed 2 of the doses are called series completed. Okay. So from here, you can see different regions. So Louisiana has 9 different regions. So from region 1, 2, 3, 4, there is some variability within the region. The mortality rate is actually higher in number 7 and number 8 region. The vaccination completed is also higher in the 9th region, but it's very high in New Orleans, the region 1, but it's moderate from region 5 and 6. So that means like there is some variability within these, different regions and the vaccination record, right? So what we have done, we wanted to see whether socio-economic condition is associated with this vaccination rate or not. That means if people are more rich, facilitated, are they taking more vaccine than people are poor and low facilitated regions? So we divided these into 4 groups: socioeconomic status, household composition and disability, minority status and language, and housing and transportation. So these are the percent. We use that one based on census data. Census has all this information. We collected the census tract. We downloaded census tract data and calculated all those for each specific census tract. We also downloaded the data from Louisiana Department of Health, and we divided this one into 4 different themes. If I go back, so the first one is called theme 1, socioeconomic status. The second one is called theme 2, household composition and disability, and the 3rd and 4th. So can we see from here, when we do a scatter plot, and we see for theme 1, theme 2, and theme 4 has a clear association, negative association with series complete, so, or vaccination. That means on the x-axis, the values goes from 0 to 1. So from 0 to 0 means people are more facilitated. Those regions has more vaccine where people are rich. If you go towards 1 on the x-axis, that means those people are actually poor, more vulnerable, and they don't have that good facility. That means they're not taking the vaccines. And from these 4 themes, you can see theme 1, 2, 4 are clearly associated. What is theme 3? Minority status and language. So we see that, okay, minority status, it's not actually associated because at the time there was no vaccination for minority people, right? So this is the overall, based on those 4 themes, we generated an overall social vulnerability index and vaccine completed. If we go through the x-axis, as I said, when people are towards 1, that means they're more vulnerable. When people are towards 0, that means they're more facilitated and rich people. So you see that when the regions where people are more poor, the vaccination gets lower and lower. There is a clear negative association. So this is actually this is called cluster map. So cluster heat map, I should rather say. So this is, we wanted to show where people are vaccinated and mortality rates by region. So the, red color indicates that people on the left has more vaccination. What's the vaccination rate? And also on the right one is like vaccination. On the left one is the mortality rate and the right one is the vaccination. So, okay, so this is actually, that one was actually, we found that one, I'm not going in depth of that one. We have actually submitted this paper in Geo Journal. So we found a very interesting cluster of association between COVID-19 vaccination and social vulnerability index. The next section, actually, I want to talk about machine learning. This is actually a talk of the topic right now. You see everywhere, you will see artificial intelligence, machine learning, computer science. People are also very interested to talk about this one. So actually, what is machine learning? How we can do, what actually it does, how it helps us to understand the data. So there are 3 different types of machine learning models. One is called supervised machine learning, unsupervised machine learning, and semi-supervised machine learning. So for the supervised machine learning, we use the label data set to train an algorithm, and we predict outcomes so that we can predict outcome accurately. So we have the overall data. Previously, what we were doing, we ran the model on the overall data. For machine learning, they divide the data into 2 groups. We call it training and testing. So 80% of the data we use for modeling, and rest 20% data, we use that one for prediction. We want to see how accurate our prediction is so that we can say that, okay, our model is working good or not. So this is actually also called cross-validation. So sometimes this cross-validation, we need to check that one because it may be overfitting or underfitting the model. So when we are dividing 80% and 20%, how we are actually dividing, who belongs to those 80% sample? We actually select that one randomly. And also we do multiple iteration so that the model will randomly take 80% of the sample 10 times, 20 times, 100 times, so that the result is robust. We have a precise result, okay? So some of these supervised machine learning models are actually linear regression, logistic regression, random forest, and support vectorization. So before I talked about linear regression and logistic regression, I didn't talk about random forest and support vectorization. So random forest is actually a classification model where you want to classify, suppose, any kind of disease group people. So suppose cancer patient, we want to classify who are actually cancer patient and who are not based on their different variables. And support vectorization is actually doing a clustering. It will divide the data into multiple groups based on some regions, okay? Okay, so that's a good question. I saw just there is a question is how is overfitting, underfitting generally. So overfitting and underfitting, like suppose you are getting value too much accurate. Like suppose you classify smokers based on cancer patients based on smokers, and you saw that your model 100% classified, you have 100 patients. You said that, okay, 50 who are a smoker has cancer and 50 who are not smoker there doesn't have cancer. So your model 100% classifies your patient correctly. That means it's overfitting. It may work here, it may not work in some other models, or underfitting, so that you saw that your model is like saying 20% of the data correctly, 80% it doesn't classify correctly. So that means it's underfitting. So what is actually good fit? That on that case, around 70 to 80% of the patient are classified true. And when you repeat that one, you see that one, and you can do based on simulation or using another data, that which one you are getting good result, okay? Unsupervised machine learning. So in this unsupervised machine learning, actually we do, we cluster and analyze unlabeled data set. On this case, we, is there any question? When we talk about supervised machine learning, we don't use any response or any predictors. we don't use any outcome. I mean, based on data, we try to classify. So suppose we have different genes for one specific cancer. We want to see like which genes are actually responsible for that specific cancer. Then we used principal component analysis or some unsupervised machine learning method to classify those patients, those genes, okay? So mostly this unsupervised machine learning we also use to reduce the dimension of the data. So suppose principal component analysis and singular value decomposition. These are two common methods for unsupervised machine learning. There is also some methods called neural network, k-mean clustering, and probabilistic clustering, so that we can divide the patients into different groups. So these are the common machine learning algorithms. They are very popular, but some of them are very difficult to explain. Neural network. So what neural network does is actually works like a brain. On our brain, it creates some nodes and it tries to link up with those nodes. This neural is actually very good for recognizing any patterns or any important role or application, including language processing, image segmentation, speech recognition, and image creation. Actually, we are using a couple of neural network methods. So this is called CNN, convolutional neural network, to identify Alzheimer's patient based on their different sulfide, nitric oxide pool, and identify how those pools are actually changing over time. Another very popular method is linear regression. Most people are familiar with that one. Logistic regression, when you have the binary outcome. Clustering. So clustering, what it does, you instead of predicting, you want to identify different groups. So suppose you say that in Georgia, I want to see different group, or out of all the counties, I want to divide them into two groups based on the similar characteristics. So then we do clustering. So there is called hierarchical clustering, k-mean clustering, probabilistic clustering. There's a different kind of clustering is available there. Decision tree, or another thing, it is called classification tree. So what it does, it creates a tree. So when you have outcome based on those covariates, it will create a tree and say that, okay, based on different criteria, how we can identify an outcome. Random forest. Random forest is also a similar pattern like decision tree, but it has it combines the results from actually the decision tree. Random forest is actually an upgraded version of decision tree. This is an interesting study that I'm going to explain very shortly. So on this data, actually, we got data from Louisiana Department of Health, Police Department, where they said that over 3 months, they got almost 90,000 calls. They wanted to see that, what kind of calls they're getting more, what time of the day, and when they get the calls, and what kind of calls they're getting most, okay? So these are different regions. So police department didn't specify, they have different regions. So they didn't specify which region belongs to which one. So based on that data, we've identified that it is SPD3. This is one police region in Louisiana, has almost more than 5,000 calls within 3 months. SPD12 is very close to 5,000, and then SPD5, SPD9, and so forth. So the first thing is SPD3, 12, 5, and 9. We identified these 4 regions gets most of the calls in last 3 months. So based on that, like we are actually getting more data from them, but from for 3 months of data, we identified 4 different regions which are getting more calls. And then we wanted to see if there is any kind of trend on these calls. And we can see that over time, there is some ups and downs, some spikes. Sometimes like the numbers are getting very high, sometimes they're going down. And we did this plot like by time, number of calls by date. These are different nature of calls that they get. Some of them are, you can see, special assignment. They didn't actually tell us what kind of assignment is that one, but they got that for that one. Maybe domestic violence, maybe some other things, we don't know. But you can see there's a couple of different kind of violence that they're getting those calls too much. But it was not our main target that what kind of calls they got. Here, this is the interesting plot. So this is called a calendar heat map. So this is what it is doing based on different time and different day of the week, when most of the calls are being people got. So if you look on Monday, or if you look on Thursday, can you see the most of the calls are within 7 a.m. to 6 p.m. So, and also most of the calls, like if you look on Thursday and Monday, there is a lot of calls from 1 p.m. to 3 p.m., especially on Thursday, 1 p.m. to 3 p.m., they are getting a lot of calls. We don't know why, we don't know, but they said that they also saw on their report that on Thursday, the crime is increasing. The number of calls are also increasing. Monday also. Surprisingly, Saturday and Sunday, there's less calls. Maybe because of the weekend, we don't know. They don't know. It was very surprising result they got. This is again another calendar heat map. Different kind of calls and what time they got those kind of calls. So if you look at special assignment, you can see most of them are actually 1 p.m. and 3 p.m. all over the week. So however, this is just to show you how different models can be run. This is actually, we have used machine learning models to identify first, reduce the dimension of the data, and then plot them, identify if there is any kind of pattern or not. So the next and the final section I'd like to talk about is called bioinformatics. What is that one? So when we collect biological data, build a computational model, solve the model, and evaluate our algorithm is actually bioinformatics. Mostly what bioinformaticians do, we have a lot of genes, all the genetic analysis, gene sequencing, RNA sequencing, proteomics, lipid profile, all those analyses are being done by the bioinformatician. What they do, suppose they identify the gene, suppose from any kind of crime scene, to collect the gene, they send it for the sequencing. Based on that one, at first they try to match, like with the criminal one thing. Suppose we want to identify any specific gene for any specific disease. Suppose right now what we are doing actually, which genes are actually becomes active for prostate cancer. How we identify the number of genes, which genes actually upregulated and which genes are actually downregulated at the time of the disease on progression. I'm going to show you something like that. So this is data we actually downloaded from TCGA website. So this data is actually publicly available. You can go to their the Cancer Genome Atlas TCGA database, and you can download this. We downloaded 400 prostate cancer patients, including their clinical RNA expression, DNA methylation, and genotyping data. We wanted to see which genes are up and down regulated based on Gleason score. So what is Gleason score? Gleason score is actually when a patient starts developing a cancer, they put or assign a Gleason score. 6 means they have just the cancer has started. 7 means moderate, mild. 8, 9, 10, moderate to severe. So as the Gleason score increase, the patient is getting more severe. And we also want to see the differential expression of the genes and which genes are actually upregulated, downregulated. Then that means the genes those are upregulated actually responsible for promoting the cancer. And those genes who are downregulated means that those are actually good genes, which are actually suppressed by those bad genes. So that's why those upregulated genes are actually bad genes. Those downregulated genes are actually good genes. But if we can somehow stop upregulating genes and promote the downregulated genes, then we can actually stop the cancer, right? So, and also, as I said, there is millions and millions of genes. So from there, we actually used PCA, principal component analysis, and reduce the dimension of number of genes. So this is actually very interesting plot. This plot is called volcano plot. On the right side, you can see those red genes, those are called upregulated. On the left side, those genes, the blue, are called downregulated. In the middle, no response, like they didn't change, they remained as it is. So here we can see a bunch of genes actually got upregulated at the time of the cancer, and also a bunch of genes got downregulated at the same time. So we need to identify, this is a lot of genes. So identify these genes is also very difficult. So from here, we wanted to see how many genes are actually common in this Gleason score. Those are upregulated. So, I mean, you can see these are upregulated genes. And for Gleason score, GS7 means Gleason score 7, Gleason score 8, 9, and 10. Out of those 4 Gleason scores, so from moderate to severe, which, I mean, or how many genes are actually in common? You can see in general, 560, 12% genes are actually common in 4 of those Gleason scores. So still like 560 gene is a lot. We need further scrutiny to identify or lower the dimension of 560 genes. But interesting thing is, out of millions and millions genes, we identified 516 common genes which are responsible or which are upregulated at the time of those Gleason scores. Okay, so this is the second one called downregulated. So these downregulated genes are actually So for these downregulated genes, you can see those are for Gleason score 7, 8, 9, and 10. So how many genes are actually downregulated and in common? So 215, 8% of the genes, they're common both in all those 4 Gleason scores. Okay, so this is a very interesting thing we wanted to identify, but still we are working more on this project to identify more or reduce the dimension more and see which genes are actually more responsible. Okay, so so this is one final slide. Why people work with the statistician? Why you want? I mean, how a statistician help to perform the analysis, like for basic science researchers? So if, I mean, this is one of the, now in USA, one of the highest paid job. If you want to be a statistician, if you know statistics, if you know, then you know data science. You talk about data science, you talk about computer science, you talk about everything. It comes actually, the baseline is actually statistics, mathematics. If you're from applied mathematics, statistics, mathematics, you can rule, you can actually do anything because that's the core of statistics. So as a statistician, what we do, how we help people, we tell them how they should design a study, which, I mean, in which way the design will be effective. The result will be like, can be published, something new will come up without losing time and money. And we have enough confidence to say that our result is right or wrong. We also help to understand how to control false positive or false negative results. So because why it is important? So think of, you want to develop a new drug, and you developed a new drug and you put it on the market. So when you develop the drug, you saw that it has some impact, but later you saw that like it has no impact. So even if you put the drug on the market, you cannot sell it, because if I take the drug, it doesn't work for me, I'll not buy it again. So maybe I'll buy it once or twice. So when the doctors see that, okay, this drug is not working, so that means when you run the trial, you got false positive result. Also, sometimes some of the drug has severe adverse effect on your health. On that case, you can think of the result was actually didn't say that, okay, it doesn't have any side effect. That means false negative, because it has some side effect. It fails your kidney, it fails your heart, it fails your other organ, right? That's why we need, we can actually, statistician can help to control that one. We also identify or help them to understand research question. So sometimes when we run the model, we started research, and over time we saw that, okay, the result is not coming as we expected. On that time, what we can do, we can change the hypothesis. So on different trials, it is called like different type of hypotheses are there. So one of them is called inferior hypothesis, superior, or equal. So on that case, if you're a statistician, you can help them to make them understand, okay, this may not be a good idea, but we can do an alternative rather than wasting money and time, because you have maybe already spent 2 years on the research. Also, we can help them to understand how to identify your primary and secondary outcome. Which outcome has more importance? We can explain them. We can get the result and show them. And finally, we can tell them that whether that study has sufficient data to correctly specify the hypothesis, or we can also help them to understand the data more accurately through visualization or addressing any kind of research question. Okay, that's a good question. As a statistician, what is the hottest path now? Actually, data analysis, biostatistics. Actually depends on you. So actually is always a talk of the topic, because if as an actual scientist, you will be working on an insurance company. But you can actuals, higher levels are very difficult because you have to pass those exams. Actual scientists, if you're really very good on math, I'll definitely suggest you can go for actuary. Data analysis and biostatistics. Okay, so data analysis, you can, if you know data analysis, you can fit anywhere, any industry. You have value everywhere. But as an actuary, mostly your job will be in the insurance companies, where they use more mathematical models to predict the insurance values, okay? And they have higher salary as you go up and up. It depends on your smartness and your capability, like how good you are. And then you can keep passing the exams and getting your salary high and high. For data analysis, if you know data analysis, you have value everywhere: hospital, university, bank, insurance. You just name it, everywhere. Biostatistics, as a biostatistician, you need, it also has a lot of, I should say scope. But for the biostatistician, what they do, they actually work with human, like patient data, biological data. So as a biostatistician, if you know data analysis, you can go as work as a biostatistician too. But actual scientists and biostat or data analysis are a little bit different in a sense. Actual scientist actually does the predictive modeling based on math. For biostatistician, they do biological, work with biological people. So on that case, you have your job in any pharmaceutical company, they pay you a lot, any industry or any hospital. So both of them actually has pros and cons. So it depends on you which one you actually choose. So that's all. Actually, this is the final slide. So, I didn't want you to teach statistics. What I wanted to give you the idea that what you can do through statistics, how it can be interesting, how you can explain your data, how you can, I mean, I didn't show any kind of maths. Right now, we are actually doing a couple of very interesting things, which is called disease progression model, how Alzheimer's patients are developing their disease, how the disease is developing over time. So a couple of things can be done, however, so that's all from me. So if you have any question, I'll be more than happy to answer.
Well, thank you so much for that presentation, Dr. Nobel. I'm going to relay now. Do you guys have any questions that you want me to put for Dr. Nobel here at this point? No? All right. So I have one that I can ask is, what do you think is for somebody that is coming out of college, what do you think is like the path if you're interested in to getting into something like being a statistician, like doing what you do, like you work with health, and that's not something that is that people don't believe is common for mathematics. So what do you think is like the path? You should go to grad school, or what you should do? What is your experience?
I mean, for me, as I was in the mathematics department with you know that. So, but as I say, if you like data analysis, if you want to be a data scientist, or, I mean, it doesn't matter what you want to be. If you want to, study math, you can study statistics. If you go to statistics, you can choose two. There are two different statistical paths. One is theoretical statistics, and another one is biostatistics. If someone is actually graduating from high school and wants to pursue as a statistician, definitely I'll suggest them, don't go for statistics, go for biostatistics. Because on that case, biostatistics is more like applied. It actually works for those people, you don't have to worry about math. Biostat, they have math, but the thing is, if you get those experience in biostatistics, you learn how to do the data analysis. But for the pure statistics department, what they do, they actually put more emphasis on only just the theories, not the applied part. So I graduated from biostatistics, and I learned a lot of data analysis through those courses. So it will teach you how to do the data analysis. So if you want to be a data scientist, you need to understand math, but moreover, you need to understand how to solve the problem, how to do the problem by coding. So definitely I'll suggest that they should go for higher studies for biostatistics. There is no other alternative. But if you want to go to actuary, on that case, I'll suggest go to applied mathematics. But to be very honest, if you are good in math or applied math, you'll be very good in statistics. I mean, during my PhD program, I took a lot of mathematics courses. So as a mathematician, actually, you are doing the harder job. Statistics is much more easier than applied math. So I think you guys have a very good future for you to pursue. Dr. Alvaro, I see some questions online. Can I answer those?
Yeah, go ahead, please.
Okay, so one of the question is, which data analysis programming language? So regarding programming language, if you're learning new, I'll suggest you go for R. R has a lot of resources, but if you interest in programming, you can also learn Python. If you know R or Python, but my point is learn one, be expert. If you choose Python, just do it in Python. If you choose R, do it in R. But don't choose two languages at the same time and then waste your time. Okay. So for me, either R or Python is good. Whatever makes you comfortable, you can do that one. And for the second question, as an applied mathematics degree, do I need to get a graduate degree to get a data science job? No. I mean, the thing is, applied mathematics, when you are taking that course, try to do some data analysis, get some experience of data analysis, do work with some researchers or work with other people, so that when you apply for a job, they want to see whether you have any data analysis experience or not. So suppose I hired an analyst a couple of months ago. So he actually graduated from applied mathematics. So what the first thing I wanted to know that how much math he knows. He said he knows. I was happy with the analysis. Then I asked him, does he know any of those programming language? He said, yes, he knows. He knows R. Excuse me. For me, I can teach him statistics, but I cannot teach him, programming and stuff. It's not that programming, you get the experience within a day. So if you are in applied mathematics graduate, I think that's a very good subject. You have a broader job market than anyone else. But at the same time, if you want to make yourself as a competitor with other degree people, you have to learn data analysis. So either you learn, and when you apply for a job, the first thing you will face, do you know how to do data analysis? You say yes. Then they will ask you which software you are going to use. If you want to join any kind of pharmaceutical company or industry, you need to know SAS. If you want to work any non-profit organization like us, health institutions, you can do R, that's fine. But again, as I said, this is a very big, broad question. So if you want to pursue your career in pharmaceutical industry, hospital, you need to know SAS. If you know SAS, it's fine. If you want to develop yourself as a data scientist, that's different, not biostatistician, data scientist. On that case, you need to know Python or R. If you want as an actuary, you need to know one of the software, that will be fine. But for pharmaceutical industry or health organization, they prefer SAS than any other language. So is there any other question?
All right. I think we don't have any other questions at this point.
Okay.
I want to thank the speaker for the very interesting topic. And thank you so much to everyone that is attending both online and here on our classroom. So thank you so much, Dr. Nobel.
Yeah, thank you so much, Dr. Alvaro. Thank you so much. Really appreciate your kind consideration. Have a good day.
All right, have a good day.